So our next speaker unfortunately cannot travel because of the recent situation, but we're going to talk about how to make analysis reproducible. So we have Dr. Chen, who is currently a postdoc at Stanford. She just moved. Her research focused on multimodal neuroimaging in neuropsychiatric disorders, combining machine learning with neuroscience to analyze fMRI and EEG data. So her talk today will explore how open science is accelerating AI-driven brain imaging by promoting reproducibility, collaborations, and addressing challenges like data harmonization and model generalization. Could you play the video for us? Thank you.
Hi everyone, I'm Zijiao Chen, freshly graduated from the National University of Singapore and moving to Stanford as a postdoc. Over the last few years, I've lived inside large neuroimaging codebases, sometimes beautiful, but sometimes terrifying. Today, I want to package the practical lessons from that too into something like an open source codebook for neuro AI reproducibility. We've come a long way since the first bits formatted dataset was uploaded. Yet, even with beautifully organized Nifty files, most AI results remain hard to 100% reproducible. Why? Because the moment you introduce millions of learnable weights, stochastic initializations, GPU kernels, and half-written scripts, you add far more moving parts than a static dataset ever contained. So here's the punchline. Data sharing is not equal to insight sharing. If I only give you my input, you will still have to reverse engineer my entire analysis stack, and chances are high that we converge on a CUDA minor version differences or a random state differences, and produce two subtly different results. So our goal isn't just about like openness for openness sake. It's to make our findings both verifiable. That means like a reviewers can literally press run and get the same number, and reusable. That means like a student can fork the repo, swap in their own cohort, and extend the science. To achieve that, we'll march through four pillars. Think of them like layers in your lasagna. We'll tackle four pillars: code, environment, data, and evaluations. Pillar 1 is the recipe card itself, transparent, verifiable code. Let's lock down a 5-point checklist that any serious neuro AI project should hit, where I'll use MyBiz as an example. So MyBiz is an FMI to visual stimuli reconstruction project. The first one is chronicle tree and naming conventions. For example, every module lives under code here, and configs under configs, experiment notebooks under notebooks folder, like pre-train and data under its own folder as well. The day you hire a new student, they should be able to guess what the loss function leaves without slack booming you. Of course, README that are actually roundable is also very important as well. It needs 3 verbs in order: install, run, and reproduce. So anyone can start to run on a clean machine with downloadable and ready-to-use model checkpoint and data. Last but not the least, we should share the training details and put it in the logs folder, which should be able to log every training run, like hyperparameters, seeds, GPU spec, training details, everything. As a result, we can see, as an example, in 2 years, MyViz earned 150 plus citation, 700 plus stars, and 100 plus votes, showing that clean code isn't just overhead, it's actually an impact multiplier. Here's how the same transparency checklist scales to a foundation model project brand JPA. So this is a self-supervised FMI encoder. So the repo here is instantly legible. Configs for hyperparameter sweeps. Source for modules, data holding the lightweight CSV indexes, and logs archiving every round's hyperparameters and matrix. Want to try this? A few bash line can help to create a contact environment, downloads a demo dataset, and launches training and evaluation. So a second line here sweeps here in the full model checkpoint for transfer learning or evaluation. That means a new lab can spend half a day experimenting that instead of half a week debugging paths. Openness also fuels visibility. In just 9 months, the repo collected 40 plus GitHub star and over 10 forks, most from the groups outside of the author's network. So the lesson is pretty simple. Clear structure and reproducible entry point turn even heavyweight foundation models into community playgrounds rather than private tools. The EPVS segmentation challenge also shows how the solid repository can turbocharge collaboration. Everything hinges on a comprehensive README. It explains the model outlook, lists the Docker requirements, and walks the participant through a fork and round workflow. The payoff was huge. Over 60 independent teams submitted models, all automatically evaluated on identical hardware. In short, a transparent, self-contained repo turned what could have been a chaotic multi-site effort into a friction-free community leaderboard. Code stays reproducible only when the runtime is locked down. Deep nets break easily. Change PyTorch 2.2.0 to 2.2.1 or tweak CUDNN and accuracy could drop. Probabilistic models are worse. One new seed or temperature and output could change. The fix here is strict locking. The good practice here is to record the exact tool. For example, what Python version are you using? What CUDA version are you using? Just lock them down in environmental YAML file. Note the hardware as well, like what GPU, what VRAM, what RAM, and also set other seeds, no matter like NumPy, Torch, from random to something, for example, like 42. For generators, we can freeze the decoding temperature as 0 and fix the top K as 0, and also set a seed as well. So with everything pinned, the results will match on any machine. Containers are the reproducibility hammer for anything that touches GPU. A Docker or Singularity image snapshots the entire software stack, from Ubuntu to Python to CUDA driver, into a single versioned file. Ship that file and your code behaves exactly the same on a grad student's MacBook, a university HPC cluster, or on Cloud H100s. No more, it crashed on my workstation, but not on your Slack threads. The digest hash is the proof of sameness. The segmentation challenge shows the payoff. We require every team to wrap its algorithm into a single container. Submissions was literally one line. Docker pushed my model. Our server pulled the image, ran the same eval script, and post scores to the public leaderboard. No argument about the driver's version, no missing library emails, just apple to apple benchmarking. Once the code and environment is locked down, data split becomes the next reproducibility landmine. In neuroimaging, cohort sizes are small and site-specific acquisition parameters, such as field strength, head coils, may produce distinct feature distribution. If records from a single hospital populate only the training set, the network might capture scanner-specific prior rather than neurobiological variants. So releasing an exact index file that fixed train validation test distribution would be important to reproduce the result. One simple example is just a simple CSV with subject ID session fold. For fair comparison, we can stratify the data by scanner size, age, sex, ensuring each fold minus the full cohort's demographic information. The EPVS challenge adopts this rule from day one. By freezing and releasing its balanced splits indexes, the organizers stopped endless argument over the lucky vote, and every submission was judged against the identical transparent benchmark. Preprocessing is the gatekeeper between raw k-space and any downstream model, and small choices may lead to massive difference in activation patterns. Slice timing on or off, both delay correction, even the brain mass threshold can swing correlation map by a large amount. Multi-site studies amplify that variance. Different MRI machines, field strength, TR setting will produce different feature distribution. The only defense is a rigid published harmonization pipeline. Best practice start with the fair pillars: findable metadata, accessible storage, bits formats, and reusable file. Every scan should arrive in a common space after identical processing. BrainJPA sets the benchmark here. The authors detailedly open source their comprehensive preprocessing information and parameters. Labs can therefore rerun preprocessing by before fine-tuning the foundation checkpoint, guaranteeing that improvement stems from the model, not from hidden pipeline tricks. Also, a single headline number rarely captures a model's true behavior. For example, MAE alone misses systematic biases. Dice score alone might hide boundary errors, and accuracy alone might ignore calibration. When outputs are probabilistic, or when dropout being searched at non-determinism, two evaluations of the same checkpoint can differ. Rep- reporting therefore means a panel of matrix plus uncertainty. So in practice, we can compute like MAE, RMSE, and Pearson correlation for regression, dice score and volume similarity for segmentation, and then bootstrap multiple times and produce a high confidence interval. We also average result over multiple physics and plot reliability diagram to quantify calibration. So the APVS segmentation challenge also followed this approach. We have a script to output every matrix, runs the model multiple times, and log logits for calibration curve. Summation ran by the full matrix set, not single score, produce a much clearer picture for real-world robustness. So that's the off pillars that we talk about. Let's land this plan with a Monday morning checklist. Your next pull list can hit all four pillars in one time. Codebase, you can move the scripts into a source folder. You can write a two-line README demo. For environment, you can add an environment.yaml file or a minimal Docker file into one digest hash with no surprise. For data, you can publish a tiny split.csv or extract preprocessing command. Even a 10 subject sample is enough to log the conventions. For evaluation, you can drop an eval.sh that prints every matrix and seed. You can bundle the lot into a container, so reviewers can literally type Docker around your image and watch the table reproduce. When we share the entire recipe, not just the dish, insights become verifiable, reusable, and exponentially more valuable. Small steps today, compounding to a culture-wide shift tomorrow. So push that PR and hit the merge. So it's time to turn guidelines into a habit. For researchers, you may pick one pillar per project cycle, maybe pin the environment this month and publish the split index next month, and let the good habit snowball. For community, let's keep funding container registered data governance toolkits and template repos. Lobby journals to adopt uniformed reporting checklists so transparency stops become optimal. So together, we can make every neural AI study a clear, citable, forkable recipe, easy for peers to verify, extend, and apply clinically. So thank you for listening, and thank you to all the team that could allow me to showcase their work as living proof that open practice paid off. Feel free to contact me if you have any question.